to BIMS TV. I'm Regina Easley, and this is BIMS Bites. And today I'll be biting into metrology for oceanography. Just to give you a little bit of background, chemical oceanography is the study of the ocean, and that includes not only the water column, but the biology and the sediments. A lot of people think about pollutants, but chemical oceanography also includes the composition of seawater, such as the salinity, the nutrients, the gases. It includes the biogeochemical cycling of elements like nitrogen, phosphorus, sulfur, and trace metals like iron and copper. And it includes climate change. And so today I'm actually going to focus on the carbon cycle. With metrology, after leaving the field, well, not really leaving the field, but in transitioning from the doctorate work to the postdoc, I started working for the National Institute of Standards and Technology. This is our nation's metrology lab. And what I've learned is that metrology is the scientific study of measurements. It is not a misspelling of meteorology, but it does help to think about areas where your measurements are metrologically traceable. So this is how do we get units on the measurements? Preferably, those units are part of the international system of units. How do we think about things like method validation? So our calibration, our repeatability of our measurements, and our measurement uncertainty. And our quality systems, like how well are our scientists trained? How do we document our processes? How do we calibrate all of the ways that we're trying to make these measurements traceable to the SI? The other thing that I've learned is that metrology is a global system, and there are literally other metrology labs that are around the world that are serving their nations the same way that NIST serves the United States. One thing that I think about a lot is the ocean carbon system. And so just to give you a little bit of background is that back in the 1950s, atmospheric CO2 measurements were being made, or they were started to being made on a regular basis. And this was done at the Mauna Loa Observatory in Hawaii by David Keeling. What they started doing in the 1980s is a group of scientists out of NOAA, they started making measurements actually in the seawater. And what they noticed is just like in the atmosphere, the amount of CO2 was increasing in the seawater as well. And what this did is it actually decreased the pH of seawater. What we know now is that the ocean absorbs about 25% of excess atmospheric CO2, and this causes what we call ocean acidification. The reason that we think a lot about this is that so many different types of organisms depend on calcium carbonate, which is a form of carbon in the ocean, to form their shells. And so the health of these organisms, ranging from things like pteropods to corals to coccolithophores, really depends on the state of the ocean carbon system. The best way to assess this system is to actually go aboard a ship and to make measurements in the water with bottle samples that are collected. The way that this is actually done is that what we call a rosette, which is a huge metal structure that has about 36 different bottles on it, is actually lowered down through the water column. The hydro wire lowers it to various depths in the ocean. It transmits data to tell you what the salinity and the temperature and the depth of this rosette is. And it can also trigger the bottles to collect water samples as it's going down the water column. You can see here, this is some of the scientists on the Arctic cruise were taking samples from those water bottles, and each one of those samples that we take, we actually, in this case, we measure in the lab that's on the ship. And so that's me actually taking the samples. And so what can we measure for ocean carbon? Well, there are lots of things that we kind of think about when we think about the ocean carbon system, and literally it's not always just carbon. There are other elements and other ions that help to buffer the seawater. And in fact, the ocean carbon system is the major buffer that helps to maintain ocean pH. The trick is that in order to measure this, we can't really measure a lot of them directly. The only things that we can measure directly are the pH and the partial pressure of CO2. We can measure the total dissolved inorganic carbon, which is a sum of a lot of different ions, and we can measure total alkalinity, which is a measure of the buffering capacity of seawater. But if we measure any two of these, we can quantify the entire system. as metrologists, things that we think about is how do we measure it? Like, what tools are people using to measure something like pH, for example, in seawater? Most labs, when they do pH measurements, they're using a glass electrode. What we know is that this doesn't work as well for the ocean because of calibration issues. Most labs will actually use a spectrophotometric dye that changes color with pH. And so this actually gives you the better precision for your measurements. The other thing that we think about is how well do we need to measure it? So what amount of uncertainty can we actually tolerate? There's always uncertainty that's associated with your measurements. So the carbon community has established various goals as in terms of what they want to assess. And for short-term variations, these are weather goals, and that has a different level of uncertainty than climate goals. Climate goals are longer-term variations caused by anthropogenic changes in the carbon system, and these need much more precise and accurate measures in order to assess their importance. The tricky part is that literally there are millions of samples that are being collected throughout the ocean, and this is done either in regional cruises, repeat hydrography cruises. The other thing that we have are a suite of different floats that occupy most of the ocean. These floats are collecting like 12,000 data profiles every month. And so that's a lot of data that you want to ensure has the appropriate quality. All has been calibrated, and they all, within a certain degree of uncertainty, will agree with each other. When the data is collected, there are a lot of different ways to visualize it, but if you're on a ship, a lot of times you take these oceanographic profiles where you look at the distribution of the various parameters from the surface of the ocean all the way to the bottom of that water column. And so once you actually have a collection of profiles, and notice that these parameters, they all change in going from the surface to the depth of the ocean, but they also change depending upon the location that you're in. When you have a collection of profiles and all of that data, what you can do is you can produce these really nice global maps that give you a state of the entire ocean. And so this is just one map that is reflecting the aragonite saturation state. So this is a form of calcium carbonate. Like, how is that actually changing over time? The trick too is that you have to have your reference material in order to, because there's so many different labs, like I stated, that are out there on ships taking measurements. There are these floats that are out there taking measurements. And so you want to ensure that your reference is back to a single place. In this case, there is one lab in the world that has produced standards that have supported these millions of data that have been collected over the past 35 years. The way that they do that is they collect massive amounts of seawater. They preserve the seawater with mercury, with UV irradiation. They bottle it, like literally 1,200 bottles per batch. And what they do is they select certain bottles from that batch to characterize a subset. And this is really great because it allows the entire world to have access to seawater that has been characterized in one place, like carefully characterized by one place, so that all of the measurements everywhere can actually agree. And that is the metrology of seawater carbon. The other thing that we think about as metrologists is if we're using different measurement capabilities, how well do the various techniques compare to each other, and the various technicians actually compare if they are measuring the same sample. So this is an example of chloride measurements that were done. And as you can see, like if you have the right procedures in place, you can actually have confidence that if you're measuring the same sample, you are getting the same answer. The way that we like to move forward with all of this is just to know that we can help to improve our monitoring of ocean chemistry even further by creating a more global seawater reference material production network. And so if you're interested in learning more about these efforts, definitely check out a webinar series that we put out. There's a video that's on YouTube where you can learn more about this. Check me out on social media, and thank you for watching. Don't forget to check out BIMS with all of the wonderful work that they are doing. And I thank you so much for your time.